Hi, I'm Dave Dugan. I'm the president of Evtron. Welcome to our presentation today. Today's presentation is on measurement for high performance buildings, but specifically we're going to talk about CO2, indoor air quality, and ventilation, and basically what's it all about, okay? So this presentation should take somewhere in the neighborhood of 50 minutes, and at the end, will be available to answer any questions you may have. Okay, let's get going. So let's just look at this real quick. I've been around for a while, and when we were in the outdoor airflow measurement business and trying to promote it in the late 80s, early 90s, we were running into a lot of brick walls. People didn't care. Even though we knew there were a lot of indoor air quality problems, we just simply couldn't get anybody interested. And then in the early 2000s, we started to see a lot of publications about air quality. And this one in particular piqued my interest because it was not just an industry article, it was a mainstream article, and it was a cover story article. And this was in Business Week, and June 5th, 2000, Is Your Office Killing You? The Dangers of Sick Buildings. And that really got people starting to think about indoor air quality. And in the early 2000s, we did a lot of work in terms of improving air quality in buildings, bringing in the proper amount of outdoor air. And then no sooner did we do that, and we started the energy folks started to say, hey, we need to bring in less outdoor air because it's expensive. And that's been happening now for the last 20 years. Okay, so that brings me to demand controlled ventilation. So what is demand controlled ventilation? Demand controlled ventilation is defined by Standard 62, okay, and it's permitted as an optional means of dynamic reset. And the actual definition of DCV isn't what a lot of people think. A lot of people think it has all to do with CO2. And really, the definition of demand controlled ventilation, or if you're in compliance, it says for DCV zones in the occupied mode, breathing zone outdoor airflow shall be reset in response to current population. Now, we seem to be always doing this with CO2. In fact, Standard 62 just approved its addendum AB, which is really heavily driven on maintaining CO2 levels. But the fact of the matter is, CO2 doesn't tell you what the current population is. So we're going to have to take a look at that. And that's what I'm going to spend the bulk of this presentation on, and then we're going to talk about methods maybe to improve it. And there's also a minimum requirement. And for DCV zones in the occupied mode, breathing zone outdoor airflow shall be not less than the building component, which is based on the floor area for the zone. And I put in parentheses there, or that required by building exfiltration or pressurization, which a lot of people seem to ignore, okay? You don't want to let your DCV outdoor air ventilation go below what you need, for instance, to make up your exhaust, okay? So that's the definition of demand controlled ventilation. The addendum AB maybe changed some of the numbering a little bit here, but it hasn't really changed this concept, okay? So when you take a look at this, what we need to do is we need to say that, if we want to know if we're in compliance, we're going to look at the breathing zone outdoor air. We're not going to do it based on the number of people in the ventilation zone during typical usage. Let's take that out. And we're going to look at it based on the current population of the ventilation zone, based on what the definition that we just went through. Okay, so it kind of turns Standard 62 into an operational standard. So the question is, what in the world does CO2 have to do with this? And what is CO2? How does CO2 relate to indoor air quality? Because I've been doing this for a long time. I mean, I've been focusing on CO2 and outdoor airflow rates, since the early 1990s. It basically was, for me, I saw, two populations of people that think it's all about outdoor air flow rates, and then there's another group of people who think it's all about CO2 levels. So let's go into this. Why do I maintain CO2 levels? And I think this, like I said, I've been doing this presentation now for almost 30 years, very similarly to what I'm going to do today. I think that over the years, I find more and more people are getting, on board and understanding this, but I still run into way too many people that don't. So I'm going to keep doing this until I feel like until we get everybody on board, okay? So why am I doing this, okay? Well, first of all, we're not doing it because it's a contaminant, and we're not doing it because it's a direct measure of indoor air quality. That's one of the first misconceptions that I see. In fact, if you look at CO2 as a contaminant, basically OSHA doesn't consider it a contaminant until it exceeds 5,000 parts per million over an 8-hour period, and in shorter periods, even higher levels, like 10,000 parts per million over a 1-hour period, is where it becomes a problem. That's not where your buildings are. Your buildings are running anywhere from ambient outdoor CO2 levels of 400 parts per million to maybe on the high level 2,000, 2,500 parts per million. So it's not a contaminant. So what is it? Why are we doing this? Okay. And the way that the industry has looked at this, and this is not correct, the way the industry has looked at this over the years is they said, hey, well, let's assume that we're at steady state. And steady state just means that nothing's changing, meaning that the outdoor air flow rate coming into the space is not changing, and the occupancy is not changing, and their breathing rate is not changing, okay? Their CO2 production rate is not changing. And we all know that when we're doing DCV, we're doing it because the population is changing, all right? Nonetheless, this is how the industry has looked at it. If you really want to look at this properly, which we're going to do at the end of this segment here, we're going to look at how the rate of change and the fact that we're not at steady state really affects how much ventilation we're getting. Okay, but we're going to do this like the rest of the world looks at it right now. We're going to look at it at steady state, and I've read a lot of papers and I've seen a lot of things where people have used a steady state assumption improperly. Okay, and I'm not going to go into that today. Okay, particularly on multi-zone recirculating systems. Okay, but when you do a steady state analysis, the volume of the space no longer matters and the rate of change no longer matters. And to make a steady state equation, it's pretty easy. The goes intos have to equal the goes outos. All right, so that box there represents our ventilation zone, and that down arrow is our outdoor air. It doesn't matter if it's coming in through a recirculated system. It wouldn't matter if it was multi-zone. It doesn't matter if it's DOAS, okay? The deal is that we would have to know how much of the actual outdoor air is coming into that zone. So you have this one goes into CO times VOZ. CO is the outdoor CO2 concentration. Most of you think of it in parts per million. I put it in as cubic feet of CO2 per cubic feet of air. It has to do with keeping the dimensionality of the equation nice and clean. Same result, no difference. And VOZ is the outside airflow rate in cubic feet of air per minute. So that's it goes into. Another goes into, which is dimensionally the same, is G times P. In this case, G is the CO2 generation rate of the occupant in cubic feet of CO2 per minute, and P is the number of occupants. We produce CO2 as a byproduct of respiration. The more of us that there are in the room, the more CO2 there is going to go into the room. So there are two goes intos. Now we only have one goes out of, and the goes out of is the same amount of outdoor air that has come in is either going to be force exfiltrated, mechanically relieved, or mechanically exhausted. So VOZ is going to be the same, but now it's going out of that ventilation zone at the new elevated indoor CO2 level, or what you would measure theoretically what you would measure in the ventilation zone. So CI. So now you have an equation, okay? And we can take that equation and we can rearrange it algebraically so it's still an equation. And one of the things that we can rearrange it for is for VOZ over P. which in, the units that would, an IP units, that's outside air CFM per person. So it's like, oh, got it now. I hope you got it now. You're not measuring CO2 because it's a contaminant or a measure of air quality. It's just simply a proxy for outdoor air CFM per person entering that ventilation zone, and there is value to that, okay? And as long as we know the CO2 production rate of the occupants, G, and the difference between the indoor and outdoor CO2 levels, we can make an estimate of how much outdoor air CFM per person is coming into the space. So graphically, we can do this, okay? We can say, hey, that blue line, which corresponds to the right vertical axis, we're at steady state and maintain 1,000 parts per million. For a given population, which is the horizontal axis, we can now make an estimate of how much outdoor air is actually coming into that ventilation zone. And so that red line is the theoretical outdoor air coming into the ventilation zone. It's associated with that left vertical axis. And, I know when you look at these, sometimes it's hard to see these graphs, but that's why I give you a presentation to look at another point, or look at now if you're following along. Okay, but these are all based on CO2 production rates of the occupant, okay, and also being at steady state. All right, now the first problem that we have, which has been a problem that we've had since 2004, okay, in 2004, Standard 62 changed the way that you calculate ventilation rates from a simple CFM per person to CFM per person plus CFM per square foot. And over the years, I've heard people say, I do CO2 DCV because it complies with Standard 62. It really hasn't. Single set point, which is what most people are doing, hey, I keep 1,000 parts per million in a space. Single set point DCV does not comply with Standard 62. It overventilates on the high populations. In this case, I'm using a school classroom, 1,000 square foot classroom, and it'll overventilate on the high end and underventilate on the low end. Technically, overventilating is in compliance with Standard 62, but you really didn't, I don't believe that was your intent. In fact, I like using this slide quite a bit for those of you that do fixed set points, 8,000 part per million control. You have some real design problems here, okay? Because unless you're in California operating under California's Title 24, which is a little bit different than in the ventilation rate required, just about everywhere else in the country is using ASHRAE 62 ventilation rate procedure ventilation rates, or IQ procedure ventilation rates, which are even lower, okay? So what I'm going to do here, taking a look at this slide, is I'm just going to use the default occupant densities for three types of spaces that are high occupant density. So I have a classroom, I have a lecture hall, and I have a conference room or a meeting space or a space of worship, okay? And at that occupant default density, okay, the calculated outdoor air required at that design occupant density for the classroom is 13 CFM per person. For the lecture hall, it's 8 CFM per person. And for that conference, meeting, or worship space is 6 CFM per person, okay? But so many times I see folks say, okay, in these spaces, we're going to maintain 1,000 parts per million. Well, 1,000 parts per million, I'm using adult males 20 to 60 years old, and it's good enough for this example, is roughly 17 CFM per person. So at the design population for those spaces, okay, you are trying to force your system to provide considerably more outdoor air than you designed it for. So if you look at that, classroom, 13 CFM, you're trying to push 17 in. The lecture hall, 8, you're trying to push 17 in. The conference, meeting, or worship space, 6, you're trying to push 17 in. What does that mean on a peak load day? It means that you can't condition the outdoor air. And in fact, when you get east of the Rockies, and we have a lot of moisture east of the Rockies, and the further south we go, the bigger the problem, we basically end up with temperature and humidity control problems, pressurization problems, operational problems. Folks don't understand why do they have water carryover problems in some of their intake louvers, particularly when there's not an economizer. What's wrong here? Well, what's wrong here is that the two things don't go together, okay? The CO2 level in the space and the outdoor air CFM per person, they're kind of codependent. You can't talk about one without talking about another, all right? And then during COVID, when folks changed they said, hey, we're not gonna do 1,000 parts per million because 800 is better. Well, think about it. Now you're going to 800 parts per million. That's about 24 CFM per person in this example. Now you've even made your systems have bigger problems. Okay, now the folks that are in dry climates in the West don't necessarily understand this problem, but the rest of us do. Okay, and so that's a problem. Then look at other things like, hey, I use the IAQP to reduce outdoor air, and I'm still trying to maintain CO2 levels. Well, obviously that doesn't work either, because you're lowering the ventilation rates even more. You might have that classroom, instead of being 13 CFM per person, 8 CFM per person. If you're trying to drive, maintain 1,000 parts per million, you're still trying to drive 17 CFM per person in. So it's a huge problem. I've been talking about this for years. The people that I get in front of and talk to finally understand some of their operational problems. And this is one of the reasons why Standard 62 is trying to make some changes through their addendum AB. I don't think they did a great job, but I think that they had to do something, okay? And that's just my opinion about them not doing a great job. I think there's a bunch of errors that I'm going to try to point out a little bit later, all right? Those of you in California, you're a little bit closer because California's 15 CFM per person requirement is closer to the 17 CFM per person. In this case, you're really not in as bad a shape, okay? The problem now is about assumptions. You've made assumptions. And how do these assumptions affect ventilation? And I was really, really happy about 5 years ago because there was an appendix in Standard 62, Appendix D, and I thought it was misleading, and it got removed, and they came out with this original addendum AB, which said, hey, you know what, there's a lot of things that affect the CO2 production rate, which essentially affect how much outdoor air is coming in, and you need to make corrections for it. And the original addendum AB was great. It was said, hey, make these corrections, determine your set point, and that's how you're going to move forward with this. Well, over the years, we had the first AB did not get approved, and it was the second AB that didn't get approved. Finally, this third AB that did get approved really is a really, really bare bones version of this. But I want to just show you this because you may or may not realize it, okay? And so the CO2 production rate of an individual is based on a lot of different things. It's based on their age. It's based on their sex. Are they male or female? It's based on their diet. Are they high fat, low fat? It's based on their body mass. It's based on their activity level. And what I'm doing here is I'm holding all males, same diet. I'm using the average body mass for that age group, and I'm keeping the activity level the same as 1.3 MET. There's folks that say, well, the younger people are more active. You can say that, but I've been in the classrooms where the 5-year-olds are napping, so I don't know that I necessarily agree with you. But anyhow, all we're going to do here is vary the age. And so we're going to calculate the CO2 production rate for each one of these ages, which you don't have to get too bogged down on this. The next column here is if I hold a difference between the indoor and outdoor CO2 level of 600 parts per million, and in this case, I'm just going to say, hey, the outdoor CO2 level is 400 parts per million. So that's 1,000 part per million nominal set point. How much outdoor air would I be bringing in for each one of these different groups of males, okay? And the 20 to 60-year-old males, there's not a whole lot of variability here, 16.4 to 17 CFM per person. The average being 16.8. I mean, I don't think that's a big deal. But when you look at the 5-year-old, it's 8.6 CFM per person. And then it gets a little bit better. And graphically, I think it's better to look at it this way. So the black line is what you needed to do to be in compliance with standard 62. And yet if you had 5-year-old males in there, you're underventilating by 36%. And I've always said to the school people, I said, did you realize that when you mandated 1,000 parts per million, you were actually mandating underventilating your young your children in schools? Is that really what you wanted to do? And of course, they say, no, I didn't know that. Of course you didn't know that. Because it's not been something that's been highly publicized over the years, okay? So at any rate, so you have this problem that has to do with the CO2 production rate just based on age, okay? And actually, this is where at California, Title 24 folks, it's actually worse. The underventilation is worse because your ventilation requirements are actually a little bit higher. Okay, so it doesn't matter where you are, this is a problem, okay? Activity level is the same thing. You know, this is a very difficult slide to see if you're watching me, all right? Because everything's so small. But basically, sitting quietly, 1.2 MET for males, office workers, 1.3 MET. Females are a little bit different. But you might have done the CO2 DCV in a workout space. So calisthenics, vigorous effort, 8 MET. Okay, you may say, well, I want more outdoor air, but I don't think you wanted this much more outdoor air. Because when you look at this relationship, you find that the MET activity level is directly proportional to this to the CO2 production rate, which is directly proportional to the outdoor CFM per person. So it's 6 times more. And I'm not very good at math anymore because I use my calculator and computer. So I'm going to just say, hey, let's just say at 1.2 MET it was 15 CFM per person. At 8 MET, it's basically 6 times that, or 90 CFM per person. You did not design your system for 90 CFM per person. Sorry. Okay? In fact, when you look at activity level and you graph it, and I only go to 5 MET here, you know, I used to say to people, you might as well go to Vegas and play one of the games. You have a better chance of winning the game than getting the ventilation right. And I actually had this graph in a paper that a little different data, but very similar, in a paper that I tried to publish in ASHRAE Journal in 2010 or 2011. And they didn't want to publish it because they said I was CO2 bashing, even though it went through peer review and was technically accurate. What do you think about that? Okay, nobody has any agendas in this business. But anyhow, I would say Dave Bitterman, party of one. Yep. Anyhow, that's the way it is, you know. There's a lot of uncertainty here. Okay, same thing is true with California's Title 24. Okay, then the next thing you got to look at. Okay, so I'm isolating uncertainties here. And okay, so now how does CO2 measurement error affect ventilation? I mean, basically, standard 62 requires that you're within 75 parts per million and on the CO2 measurement in the space, and says you can assume 400 parts per million outdoors. Well, I don't have time today to go through all the data, but I have data that shows CO2 levels outdoors anywhere from 350 parts per million to 550 parts per million, depending on the season, depending on what's going on. There could be a thermal inversion. There's a lot of things that affect CO2 levels, time of day in cities based on vehicles. A lot of things affect the outdoor CO2 level. Indoor CO2 level, it's not just the measurement error of the sensor, it's the placement of the pickup point. If you come to Ebtron, we have a brain guest room, we call it. It's a 5,000 square foot space. I have 12 CO2 sensors in that space that when they're together read relatively the same, okay? But operationally, when I put people in that space, those 12 CO2 sensors can read 100 to 200 parts per million different just based on where they're located. okay? And that has nothing to do with the measurement error of the sensor, okay? So this graph here that shows the scatter is basically what happens if you recalculate everything, but you had these errors in your measurement. So where the red line had been your theoretical ideal line, okay, the red scatter is with the 100 part per million uncertainty on the indoor CO2 measurement and 50 part per million outdoor. And this is if all of your other assumptions are right, meaning that you're at steady state, which you're probably not, that you actually knew the CO2 production rate of the occupants, which you probably don't. Okay, all right, and so those are the problems here, all right, and so lots of us. I mean, look at that. The black is what you needed to provide, okay, so that at 35 students there on the far right of that horizontal axis, the black intersecting point is how much outdoor air that you needed to bring in, and the highest point on the scatter is how much outdoor air you may have brought in or you would be in CO2 alarm, and that's 50% off. Your systems can't handle 50% over ventilation. I mean, you might say, oh yeah, that's great, I don't mind the over ventilation. Well, your system can't handle it, okay? It wasn't designed to handle it, all right? So you got wasted energy, you got thermal comfort issues, you got pressurization problems, and on the other end you might have IQ problems or pressurization problems. Okay, and same deal here with Title 24. It's just, it's not a good situation, okay? Wasted energy, thermal comfort issues, same deal, okay? All right, so now you say to me, Dave, you've been fighting this for 30 years. I'm not gonna fight this. I have to do this. I have to use CO2. So what are we gonna do here? Okay, so the question should be, can I improve it, all right? And the answer is yes, we can improve it, okay? And the first thing you need to do is account for activity level and age, and then you need to set some limits, okay? Now, how do you set limits, okay? And most people set limits with fixed dampers, but we can demonstrate that fixed dampers, you have problems with them, whether they're on recirculating air handling units or you're doing DOAS with zone level measurement, you can't rely on a fixed damper position, okay? All right, there's just, on recirculating units, basically we have wind pressure and stack pressure that we have to deal with. We have hysteresis, binding, deterioration of the damper. Those are problems, okay? And then, we don't have the wind and stack pressure problem when we talk about DOAS, but on DOAS, we have different zones, ventilation zones, that are changing their ventilation requirements so that a given damper position will result in variability in airflow. So you just can't set fixed damper positions, right? So I show all this uncertainty on the damper, it's useless. And I'm not even showing you, like on a rooftop unit or something like that, the fact that there's additional error because test and balance can't even get out there and get a good measurement, okay? And then on top of it, you have this either changing fan speeds or changing damper positions on DOAS. So fixed dampers don't work. It's a moving target. You cannot rely on fixed dampers. All right, the way you need to do this is you need to do flow measurement. On recirculating units, it's in the outdoor air intake, and DOAS, it's at the ventilation zone, okay? And a very common way that people would do this is they would do a deadband control where they would set a min-min and a min-max, and they would control at the min-min or the min-max, depending on what the CO2 level in space is. And if you're doing it with airflow measurement, it's a big improvement. Now, I am going to show you some of the real-time lag problems, but it's a major improvement, and that's what you should really do. The preferred way that we've had to do it for years, that I think in reality, Standard 62AB is finally saying to do this, even though they don't explicitly say it. This is what they're saying. okay, you measure the CO2 level in the space, okay, and you look at your CO2 set point that you're trying to get to or not exceed, okay, and you basically, it goes into a control loop or reset loop, and you output a new airflow set point, okay, and then you compare that airflow set point to your min and your max. If it's below your min, you set it to the min. If it's above the max, you set it to the max. If it's anywhere in between, it's anywhere in between. And that airflow set point then goes into your outside air control loop, which could be as simple as modulating a damper or a more complex sequence that's required on some air handling units, okay? And you end up with this within the limits of the airflow measurement error, okay? So this is a significant improvement. And that just brings me to this addendum AB, which, like I said, it's just recently approved. Probably most of you don't even know it's been approved, okay? And so, you know, a couple things that I want to state that what they're telling you to do now, which is an improvement, but there's some problems that I'm going to explain to you, particularly when we go into actual operating, meaning we're not at steady state, okay? But at any rate, they say DCV controls to maintain the zone ventilation rate no less than the building component when zone CO2 concentration is at its ambient or low outdoor level, basically. Upon a rise in measured CO2 levels, ventilation shall be increased proportional. So it's a proportional reset. It's not the perfect way to do it, but it is a better way than that deadband control that I showed you previously, okay? And so it's a proportional reset. This statement here is not correct. Because CO2 and ventilation are codependent, this will rarely, if ever, happen. And I am concerned about the language on this. It says, when the zone CO2 concentration is equal to the maximum CO2 concentration, the minimum zone ventilation rate shall be equal to its design ventilation rate. That is not necessarily going to happen. And I'm going to show you that in a few examples. Okay, but anyhow, Addendum AB is an improvement, okay? It does, you know, one of the problems that I've had getting people to do our method that we've wanted to do is that you'll end up with a CO2 level in the space that varies. People weren't ready to do that. Well, now if you follow Addendum B, that's exactly what will happen. CO2 level in the space will vary. There's a couple other things that I think are noteworthy here. And it kind of helps with this one problem I'm talking about. Zone and system ventilation rates are not required to be larger than the design ventilation rate required by Section 6.2 at design occupancy, regardless of CO2 concentration. And that has a lot to do, I think the intent here was they knew there's going to be measurement error, but it's also because of this codependence problem, okay? So that, you know, you have an airflow measurement device in either your outdoor air intake or at the ventilation zone on DOAS, and then, you know, you basically can say, hey, the CO2 level is higher than my set point, but you know what? I can show that I'm at the design maximum. That's great. And I was glad to see this note because I think this was very important. The CO2 values in Table 6.1, which I'm not showing you Table 6.1. Unfortunately, they give you they give you CO2 default levels, which are rarely, if ever, going to be what the correct CO2 level needs to be on a lot of these spaces, okay? And unfortunately, not everybody's going to understand that. They're just going to look at these CO2 levels and set them, okay? The other problem is they allow CO2 to be used on low occupant density spaces, which I'm going to show you is a very, very, very bad idea, okay? But anyhow, the informative note that I think is good, it says the CO2 values in Table 6.1 are only for the purposes of implementing CO2 DCV. They are not intended to be and should not be used as indicators of IAQ. That's very interesting, but very true. So then the next thing comes up, is there a better way to use CO2? Okay, and I think there really is. And this is really how I had wished that Addendum AB would have been written in terms of how you do the control. Because, you know, Standard 62 rarely tells you how to do something. They don't tell you to measure outdoor airflow rates and control them, but for some reason they're telling you how to do the CO2 DCV, and they're not even telling you necessarily the correct way to do it. Okay, but when you take a look at the steady state equation, if you're going back and you're making the assumption of steady state, which is again what everybody's doing, which is wrong, okay, and you are measuring, if you were measuring the outdoor airflow rate either at the air handler or to the ventilation zone, okay, in DOAS, you actually have one more piece of this pie, and when you have that one more piece of this pie, you can estimate the population. And again, we've been saying this. I've been trying to tell people to do this for 15 years. I don't know why nobody listens. Okay, but basically, if you have, if you know the CO2 level, you know the outdoor airflow rate going into the ventilation zone, you can estimate the population. And I just showed the logic here. You measure the CO2, you measure the outside air, you calculate the population. It's very easy to implement on single zone. That's what I'm showing you here, or on DOAS. You calculate the required outdoor air for that zone. Again, establish the limits. If it's less than min, set to min, greater than max, set to max, in between, it's in between. It goes into your outside air control loop. And that results in this, which for those of you that are working under Standard 62, or the VRP, this is a really good way to do it, okay? All right, I'm going to step out for a second here. I'll be right back. I want to look at the steady state assumption errors. I got some examples, all right? So I'll be literally right back. Okay, I told you that would be fast. So now we're going to take a look at some examples. And the examples are going to be a little tricky to look at, okay? Basically, some of this is material I've just kind of put together recently based on some old material I had. And it's not best suited for a presentation of this type. If you want to take a look at the individual slides, I think from the file that we sent you, I think it'll be better, okay? But just follow along with me. The fact of the matter is we're not at steady state, and we have to take a look at what that really means in terms of the ventilation that we're providing. All right, so what I've got here is we're going to look at a couple examples. I have lots of examples. We're going to look at a classroom example and an office example. In the classroom example, we're going to look at two populations. We're going to look at the design population and a lower population. The office, we're going to look at design population. Okay, and when you take a look at these two charts, okay, all right, the top chart is basically showing you outdoor air CFM per person. That's either assumed, required, or provided. I don't have the required there. It is the green line because I just didn't want to get the arrows all too tight together. I mean, assumed and provided is what I want you to see. The bottom graph is the total outdoor air required and provided, okay? The other thing I want you to look at is that the red dashed line is the instantaneous amount of outdoor air that you are providing, and the red is the time average over 1 hour, which is what's required by Standard 62, okay? And so those are all associated with the left vertical axes, okay? The horizontal axis is time. We're not going to have the students go in and out of the classroom. It does make a difference, but I don't think it's important for this part of the discussion. The right vertical axis on the top is how many people are in the space, and you see it's 30 on the top. If you can see that small print. And on the bottom, it's the actual CO2 level, okay? And so I just want to go through this with you, all right? So this model that I have has the ability to bias the CO2 measurement. It has the ability to bias the outdoor air CO2 level. It has the ability to bias the CO2 production rate. It has the ability to bias the actual min and max airflow rates or measurement accuracy that you're using, or the effect of using fixed dampers. But in what I'm going to talk about today, you don't have any errors. We're just looking at, if everything was perfect, what's the lag effect, okay? And that's really one of the problems with all of this, is that there's so many variables. To get this across and people understand it, it's not that straightforward. Bottom line here is we're trying to provide the proper ventilation for a given population. Are we or aren't we doing that, okay? All right, well, when we do this two-position deadband control that's very common, that folks have been using for years, we don't do it, okay? Clearly don't do it. There's a lag problem of about 1 hour. If you're looking at that bottom graph, the provided outdoor air is significantly less than the required outdoor air for the first hour of occupancy, okay? And that's the average. I'm looking at the average outdoor air provided, okay? It's low. All right. The other thing that's important for you to understand, and one of the problems that I have with everything here, is just because you're bringing in the design outdoor air rate for standard 62 doesn't mean you're going to hit your CO2 set point, because they're codependent. In this case here, the set point's 1,000 parts per million. But if you look at that right, you look at the blue on the bottom graph, and goes with the right vertical axis, we're over 1,100 parts per million. I mean, that's allowable by the standard, but it's going to confuse people, because you're not going to be able to get to 1,000 parts per million at the design occupancy, at the design outdoor air, in this particular example. Okay, so that's the bottom graph. On the top graph, there's a couple problems here. I show the outdoor air, basically the top graph is outdoor CFM per person. What you provided is clearly low, but there are people out there that believe that you can tell how much outdoor air CFM per person there is coming into a space simply by measuring the CO2 level. That is true at steady state. It's not true when you're not at steady state, okay? And so when you take a look at this, if your calculated outdoor CFM per person is really high because your CO2 levels were really low. And you're like, oh, this is great, I have lots of outdoor air. No, you don't. You significantly underventilated this space for the first hour of occupancy. That is not a good situation. Now, when we go to the next example is using the proportional reset that this addendum AB has recommended. Okay, well, the proportional reset, okay, is still going to underventilate for the first hour. There's no way around this. Everything's based on steady state, okay? The values are a little bit different in the beginning. This is a slightly better method, okay? But it's still going to underventilate for the first hour. And then we look at the third one, which is our estimate using, estimating the population. It also underventilates for the first hour, okay? So none of these really meet the requirements of Standard 62, even though Standard 62 has said this is what you have to do. This is one of the problems when a standard starts telling you how to do something, okay? It's simply, there's no way to provide the required outdoor air, okay, using CO2 because of lag, all right? So this is at the design population. Now, the real problem we've had is when we're off design, okay? So here's the same classroom. Some people would say to me, well, it's a public school, it never gets off design. Well, there are spaces in the school that do go off design, and people are doing this in university spaces and college spaces, which are often off design, okay? So now take a look at this, all right? Now, instead of having, instead of having 30 people in this classroom, I have 10, okay? And so I've reduced populations, and this is one reason why I should never do this during COVID, okay, if you have reduced populations, because you're really going to underventilate. So if we look at the bottom graph, okay, the required outdoor air is the green, okay, and the provided outdoor air is the red, and you never reached the required outdoor air. You never provided the required outdoor air using this two-position deadband control that we've been using. And in fact, you significantly underventilated for the first almost 2 hours, okay? Your CO2 levels look good, but you weren't providing the proper ventilation rate. When we go to the standard 62 addendum AB proportional reset, and I can explain this to you if you want to know outside of this conversation, because the proportional reset actually has a tendency to provide more outdoor air between the min and the max. What you see here doesn't really look too bad at the low population density, meaning we actually are providing the required outdoor air, and in fact, most of the time we're providing more than we needed. When we look at our population estimation method that we prefer, it actually does underventilate a bit. Now I do have some methods that we can improve on this with, but today I'm just trying to show you the problems that you have, okay? So that's on the classroom. So now offices, that's something that really bothers me, because in the addendum AB put in a 1,000 part per million set point for an office space. You have a low population density, okay? It takes a long time to get to steady state, okay? So in this case here, we basically when we're trying to do, this is at the population, the design population was 5 people per 1,000 square feet, and we were at 5 people per 1,000 square feet. So this is like the best case, okay? And we're using this to control ventilation in office space. We underventilated for 3.5 hours, and we significantly underventilated. Okay, if you look at the provided versus the required on the lower graph, we significantly underventilated. Okay, and again, that's a problem. Now this is with the deadband control, okay? But it's not really any better with the addendum AB recommendation of just a proportional reset, and it's not really any better with the version that we like, which is estimating the population. The reason for this is we're not really at steady state. It takes a long time to get it to steady state when you have a few people in the space. I don't understand why folks don't seem to understand that, okay? And yet again, if you were using, go to the top there, and you didn't understand this relationship, and you just simply went by the CO2 levels, you'd say, ooh, look at all this outside air I'm bringing in per person. It's not real. That's not what you're really bringing in, okay? So these are serious problems. It always brings me to this. It's like, there's gotta be some agenda here, okay? Because the standard clearly says, provide the breathing zone outdoor air for the population. But yet there's no research, no significant support for counting the occupants. Why? If you counted the occupants and you measured and controlled the outdoor airflow, whether it be on a recirculating system or a DOAS system, you'd be done, okay? Why is there no support for this, okay? I mean, you say, oh, you can't measure it. Of course you can. I mean, there's plenty of counting systems today. COVID actually improved that. There's a lot of good counting systems. We even make a counting system, okay? There's ticket counting systems, arenas, convention centers. They know how many people are in these spaces. I used to say casinos were the only ones who could use video imaging counting systems because they were expensive, but they've actually come down in price. Point of sale, why a movie theater? Like, why is a movie theater controlling the CO2 when they have a point of sale system that tells you how many people are in each space? It's the ideal way to do it. You know when a movie starts, you know when a movie ends. It could be any kind of theater, but you know when it starts, you know when it ends. It even works out well for multi-zone. Why are we not, multi-zone recirculating, why are we not supporting this? There's gotta be a reason, okay? And so I always tell people, think outside the box, okay? And when you do population-based DCV, it's really simple, right? You count the people, standard 62 is based on people, do the calculations, set the limits, control it, okay? You end up with this. I have a 3-person uncertainty on that class, 1,000 square foot classroom, 30 students in it. I go up to 35 here. I show 3-person uncertainty. That looks pretty good, and there's no lag error. I just don't understand it. I mean, I understand it, but I don't understand it. Yeah, a couple good things though. Also, in addendum, maybe I did want to point this out at least. Maybe we can get people to do things better. I skipped this when I showed this slide previously. Other DCV control logic shall be permitted to be used where it can be demonstrated to comply with section 62611 under all expected operating conditions. Yeah, that's provide the breathing zone outdoor air for the population. So yeah, you can do this and meet the requirements of the standard. That's a good thing. Okay, thank you for attending. We're going to be available to answer your questions right now if you have any. Also, if you have any questions that you think about afterwards, just send them to askdave@engineeredsalescorp.com and we'll get back to you. All right, thanks again. Take care.